Hey, hello, Physics 122 students. I thought I would make a video solution here of last week, the chapter 27, number 22. It says it's a review problem, and I thought I'd make the video partly because I had a couple questions, but partly I began to realize that this would be a little bit of an unfair question for half of you, because the review goes back to chapter 19, where chapter 19 about thermal expansion. And so we're learning in this chapter that if you warm something up, the atoms shake more and therefore have more resistance. But there's something else that happens. When they shake more, they bump into each other and they get bigger. So there's what we call thermal expansion. Now, all of you probably saw that in your previous physics course, whether that be our local Physics 102 or whether you took that in high school. You probably came across thermal expansion, but you haven't really done it in our series of Physics 121, 122, and 123. At least half of you haven't, because we cover that in chapter 19. And so that's for the spring semester. So some of you took it last spring, and half of you will take it this coming spring. So let me work through this one. Here's what it says. It says an aluminum rod has a resistance of 1.234 ohms. All right, so I'm just going to kind of draw a metal rod. Oh, and I just realized I got my COVID bracelet for campus today on. So, well, I'll take that off later. But you can then tell it was Monday here on campus, and so I got my COVID pass. All right. But here is our piece of aluminum, 1.234 ohms is the resistance. Okay, so that's the resistance of our piece of aluminum. But as I said, when the aluminum warms up, and I should say this is it at 20 degrees Celsius. And so one thing we're learning in this chapter is you can't really talk about the resistance of something unless you also say what temperature, because it does change with temperature. And then likewise, you'll hear me say this in the spring, or you did last spring, is that you can't really talk about the length of something, L, and its diameter. Why don't I just call it the surface area as the current tries to flow through here, okay? But this surface area would change also. And so when the atoms start bumping around, like I said, they're going to bump. It's going to make it longer. It's going to make a bigger diameter. And it's going to make it harder for electrons to get through all these shaking and jiggling atoms. So we know that the resistance is rho times L over A. And of course, at 20 degrees, we know that that comes out to be 1.234 ohms. That's what the problem says. But then it says, go ahead and calculate the resistance of the rod at 120 degrees. So that means we're going to warm it up. I'll just put delta T then, is going to go 100 degrees. We're going to increase up from 20 to 120. By accounting for the changes in both the resistivity and the dimensions of the rod. So coming over here, maybe I will recalculate the resistance. And so let me put resistance underneath. I'll put 120 degrees Celsius. So this would be the temperature increase due to the resistivity, which we said was 1, oops, that's not a 1, 1 plus this alpha delta T. Now, let me pause there. Actually, why don't I grab the book? Yeah. Okay, here we go. So, grabbing the book here. Oh, good. Chapter 19. That's what I want to come back to in my second thing. All right. But this chapter, chapter 27, this would be a good point to say, we have this coefficient, right? This coefficient is how much the resistivity increases for each degree. Let's see, where do they write it? So somewhere in here, maybe they do it a little later. Well, they put it here for the resistance that's incorporated. Well, up here, here's the resistivity. And so it's this alpha, and that's what this coefficient is right here. So, oops, so I didn't do a very good job of centering that up on the book. All right. So this is that resistivity chart. So they say it's aluminum, 1, 2, 3, 4, 1, 2, 3, 4. So right here, 3.9 times 10 to the minus 3. Okay. So that is this number. 3.9 times 10 to the minus 3. Okay, and then of course we're going to increase it by 100. Now, here's where this problem, like I said, is perhaps a little unfair, because coming back here and where I flipped the book here at the beginning and probably didn't align the book so you couldn't see, but in chapter 19, okay, we start doing some thermal stuff, if you will. And we have what is called here the linear expansion coefficient. And it also has a symbol of alpha. And maybe that's too bad, because that could easily be confused. But on the page before that, which I guess would be over page 538, we can see that the length increases by this factor. The delta L is this alpha times the original length times delta T. So that's the stuff that I need to show those of you who have not gone through Physics 123 yet, so you can understand the problem better. And so what I'm going to do is then say that the new length would be the old length, and then the same thing. It would be 1 plus an alpha delta T. So the L times the 1, that's the original length, and then the L times this alpha delta T would give me the alpha L delta T that I was just showing you coming from Physics 123, that the length increases because of this jiggling around. Now, it is a different alpha. And so I think that's why some of you emailed me, is because you saw the alpha in the equation and where you were thinking it was the alpha for the increased in resistivity. It's not. This is the expansion of it, the linear expansion coefficient. So for aluminum, it's 24 times 10 to the minus 6. So I'm going to put here 24 times 10 to the negative 6. And by the way, in case anybody is wondering, note that the increase in resistivity right here is something like 100 times bigger than the thermal expansion. That is the expansion of how much did it grow by. And so, in case you're wondering, that's kind of our justification of why we often ignore it getting bigger and smaller. It's not just that some of you haven't done it yet. Okay, so this, I'm trying to think of the name of it. Oh, the temperature coefficient. That's what they call that. So this is the temperature coefficient of the resistivity, and this is the linear expansion of it. And you can see here that this plays a much bigger role. Okay, now the other piece of this would be the fact that the area gets bigger. And that would be then some radius that it originally had, squared. But the radius would grow also by this 1 plus alpha delta T. Okay? And that's, I guess, right here would be this pi and then the r squared plus a1 plus alpha delta t squared. And again, this alpha is how much it grows in size from the aluminum. And you can see that there's two of these factors and one on the top. So one of these factors on top is going to cancel with one of them on the bottom. So if we simplify all this math, we get our original resistivity at the 20 degrees. We get our original length when we were at the 20 degrees. We also downstairs have our pi r squared, which is again our original length at 20 degrees. And what we're left with is in the top is a 1 plus alpha delta t. And so I'm going to put a little e here for the electronic alpha. This is how much the resistivity increases by. Okay, this is the temperature coefficient. But it's not the temperature coefficient of expansion. That's what this is. And one of them canceled off, so the other one is still down here, 1 plus alpha delta t. And this is a thermal expansion one, so maybe I'll put a little t under here. All right, then fortunately, this isn't too hard to calculate because these original numbers are what we talked about at the beginning up here. This would come out to be the 1.234 ohms because that's all the stuff at 20 degrees. So then it would be increased by 1 plus, and so as I said, this is the electronic one, 3.9 times 10 to the minus 3 times 100 degrees. And the bottom would be 1 plus, and then this would be 24 times 10 to the minus 6 times 100 degrees. And again, you can just pretty much ignore that one. And so that's, again, probably a better argument of saying, look, we're not going to worry about the wire getting longer or thicker. Of course, when you factor in the two of those, the fact that it got thicker has a square to it. So the thickness actually makes the resistance go down. But it's dominated by the resistance going up just because of the electronic nature of it. All right, so this number here would be a 1 plus 3.9 times 10 to the negative 3 times 100. So there's the numerator. And this is 1 plus 24 times 10 to the negative 6 times 100. And see, that's what I was trying to say here, is that the increase in the resistivity is, very reasonable number. I mean, that's a 39% increase right there, because, we go from 1 to 1.39. But the reduction here by the denominator factor, is not even 1%. It's 0.24%. So we really could just ignore the change in the length. But this is a good problem to see that. All right, so let me take that numerator and divide it by the denominator. And so it does cut it down a little bit, but there is an increase. So let me take that number and multiply by 1.234, coming up with a 1.711 ohms. Is how much it's going to be now. So definitely goes up. And in fact, like I said, if you did not include the growing of its length and its diameter, you still would get a number really close to that. I think that would come out to be 1.72 instead of 1.71. So that's the idea of this one. All right. Hope that helped.